everybody. Today we are going to discuss the new chapter, complex integration. That is actually about in your syllabus. It is said about the contour integration. Hmm? Basically, what is contour and how does it? How is it related with this kind of complex numbers? And that I shall discuss today. And mainly today I shall have to discuss some definitions related to this contour integration. Hmm. This is the chapter number 8 in this book, but as per your syllabus, this is the next immediate unit after analytic functions. So over here, we shall have to discuss the geometry of a contour. And in order to discuss the geometry, let me start with this sheet. Over here, suppose let us discuss this kind of space. Okay, not this kind of space. Firstly, a two-dimensional space. The Argand plane in two-dimensional space. You see, if this is suppose positive x-axis and this is our positive y-axis, then we know that any point on this kind of plane can be considered as a complex number, and a point on this kind of plane can have this kind of representation x comma y, and in terms of complex number this representation can be written as x plus I into y. We call it the complex number z. Now today we shall firstly discuss about certain curves in this kind of complex plane. So in this kind of complex plane, by curve what we mean this kind of line, maybe this kind of line. And you see, if you consider any point on this kind of line, maybe its coordinate is x comma y. Then the coordinates, suppose this is the point, say capital P. Okay, having coordinates x comma y. You see, in that case, the coordinates of the point P, they are changing from maybe the initial point capital A to the final point capital B. Suppose the point P is changing its position starting from this initial point A and moving towards the point B along this curve. Suppose let us call this curve the gamma curve. From A to B, the point P is following this kind of curve. This is the curve gamma. Now you see, in that case, the coordinates of this point P, they would ultimately change. And how would they change? They would actually, this x would actually be some function of a parameter. Function of, let us call it the parameter t, and y would also be a function of a parameter p. Okay, so x and y, these are this may be function of a parameter t. Remember, do not mix this parameter with the parameter time. T may be any arbitrary parameter. Okay, and over here, suppose at this point capital A, the maybe this is the position of the point capital A, and maybe this is our the position, the coordinates, maybe coordinates of the point capital A may be x0 y0. And in that case, the value x0 would appear, this x0 would appear for certain value of t, let us call this value as t0. Similarly, y0 may appear for the same value, so we write it y of t0. So whenever t is equal to t0, we obtain this kind of point, capital P. And maybe you can also consider t0 is equal to maybe our small a. And maybe at the point say tn, let us call it small b, we obtain this kind of coordinate. That means b, this point b can have this type of coordinate like xn at the point t is equal to tn. Say that these are the coordinates, suppose xn and yn. Then what is xn? You see xn b is equal to x, the value of the function x at the point suppose tn. And yn, suppose this is the value of the function y at the point tn. Okay, and you can also consider, as because we have considered tn is equal to b, so you can also write this expression as x of b, and that would be y of b. Okay, similarly over here in the initial point, this can also be written as x of a, and that would be y of a. So what we observe is that, suppose this picture, let me elaborate this picture in this way. Say this is the curve from a to the point b, and you can consider this kind of axis. Suppose this is the t-axis. Over here t is equal to a and t is equal to b. So a less than is equal to the parameter t less than is equal to b. Do not mix this axis with this x-axis. With this x-axis, do not mix this axis with this x-axis. That's why I did not write the t-axis over in this picture. So for t is equal to a, this t is equal to a is related with this initial point. T is equal to b is related with this final terminal point. And intermediate points for each and every such choice of value t, we will get certain intermediate point like this. Say like this. Say this kind of point. So in this way, you will get different coordinates of the of this curve gamma, for different choice of this parameter t in between a and b. All right. So these are actually this representation. Over here, this representation is actually called the parametric representation. This representation, you see, this representation is called the parametric representation of this curve gamma. X is equal to x of t, y is equal to y of t. This representation is called the parametric representation of this curve gamma. So that is the idea of a curve in a two-dimensional plane x comma y, or you can consider this one as a curve in the z plane or this argand plane. This z plane is actually also known as argand plane. So that is the idea of a curve in this z plane or argand plane. Let me continue with this idea, and we'll have to introduce certain definitions over here. What kind of definition? We shall firstly need to introduce the idea of partition. Okay, so first one, we need to introduce the idea of partition. Partition. What is this? Partition of this kind of interval, the interval of the parameter t. Suppose we divide this interval a to b into finite number of subintervals by introducing this kind of point. Say, suppose over here we already have this a is equal to t0, and intentionally I have introduced t0 and tn, and actually my target is to introduce certain few numbers t1, then t2, and so on, dot dot dot, hmm, less than this tn. Okay, the first point, this is our t0, this in the first initial point. Then the next point is t1, then t2, and so on. This is our tn minus 1, and the last point b is equal to this tn. So over here we are dividing this AB subinterval into finite number of subintervals, and this collection of subintervals is called the partition of the interval AB. Partition of the interval AB. Sometimes this collection of points are also termed as partition. That means these points T0, T1, dot dot dot, say Tn, these points are also referred to as the partition of the interval AB, because of the fact that using this kind of point we will be able to subdivide this interval. We will be able to subdivide this interval of AB in, and number of intervals should be finite. Okay, so this is called the partition of the interval AB. And most of the times we denote this partition by the notation capital P. Although I have introduced this arbitrary point as the notation capital P, but for the time being, let me forget this arbitrary point P. And then this interval AB, this one, this is called the partition of the interval AB. Okay, so for the time being, let me just delete this point. So this is called the partition of the interval AB. And what are the length of this kind of each and every such interval? You see, if you consider the rth subinterval, what is rth subinterval? The rth subinterval is tr minus 1 comma tr. That would be the rth subinterval. And what is the length of this rth subinterval? The length of this rth subinterval is tr minus 1. So this is the length of all this. All this is the length of the rth subinterval. So let us write it as delta t suffix r. And now, if you consider this kind of in lengths, then delta t1, that would be the length of the first subinterval. Delta t2, that would be the length of the second subinterval, and so on. Similarly, delta tn, that would be the length of the last subinterval. Okay, and in this way, if you consider the maximum of all these subintervals, the maximum of all these subintervals, then that maximum value is called the norm, NORM, norm of the partition P. Okay, and norm of the partition P is sometimes designated by this kind of notation. Let me write it in this way. Norm of the partition P is sometimes represented by this kind of notation. This double bar is the notation of norm. Although the book I am discussing over here, they have just simply used this modular notation. Whatever be the notation, it doesn't matter. Norm has this kind of notation, that is actually the standard mathematical notation of norm. So in this book they have used this kind of modulus of p. You can use this one. You can also use this kind of norm notation, the double modulus notation. Okay, so this is actually the standard mathematical notation of norm of any quantity, and the idea of norm is actually related with the length of certain quantity, and that the detail about the norm you will discuss them in your higher study, that is especially related with the idea that is called the length of certain quantity or the weightage of certain quantity. Not length, I would rather say the weightage of certain quantity. So this much I can say about the norm. But over here, norm of the partition P means the maximum of all this length. The maximum of this length of these subintervals. This is called the norm. And sometimes this norm is also denoted by simply delta. And what is the use of this utility of this kind of norm? You see, the utility is that if you take the norm tending to 0, this kind of limit, if you take the norm tending to 0, norm means the maximum value of this delta t1, delta t2, delta tn. So as because this is the maximum, so we can say that each and every this delta t r, each and every delta tr should be less than is equal to the corresponding maximum value, that is less than is equal to the norm of p. Therefore, again, this each and every such intervals are all greater than is equal to 0. Therefore, if the largest quantity is tending to 0, then each and every such delta tr, you see, each and every such delta tr would tend to 0. If the largest quantity is tending to 0, then each and every such delta tr would tend to 0. And in our study we shall require this kind of limit where delta is tending to 0. In the definition of integration we shall use this idea that delta tending to 0. In that case we can say that this delta t, each and every delta tr, each and every such delta tr would tend to 0. And delta tr tending to 0 means this in length of this intervals should be very small, very small, and so small that it is tending to 0. That means we can say that in that case n, the total number of subintervals, that would tend to infinity. So delta tending to 0 implies delta tending to 0 implies that n tends to infinity. Delta tending to 0 implies that n tends to infinity. This is not r, so it looks like r. N tends to infinity. Okay. So delta tending to 0 means number of partition n tending to 0. But converse result is not true. You see, if n is tending to 0, n tending to 0 means the number of partitions should be larger than n is large number. You see, over here we can divide one single subpartition so that n tends to infinity. So it does not mean that delta, maybe this is the length delta, maybe this is the length delta. It does not mean that delta is also tending to 0. Okay. So over here, remember that the converse result is not true. So delta tending to 0 means the number of partition or n, this n is tending to 0. Okay. So that is all about the idea of partition and its norm. So
Sir,
now, yes, any question?
sir, is norm less than zero always?
No, why? Norm is greater than is
So
equal to 0. Why is it less than 0? Did I ever write norm less than 0? You see over here,
less to
this,
zero from left hand side or both right
no,
hand
no,
side?
no. Over here, you see, over here, this is the restriction that length of delta t would be greater than is equal to 0. And maximum of such length is equal to the norm. So norm is itself a kind of length, the maximum of all this kind of length. So length can never be equal, never be negative. Length is always positive. Okay, so
Oh, yes,
we
sir,
should
yes.
keep in our mind that norm, this delta would always be greater than 0. Hmm? So we should write delta tending to 0 from right side. Okay.
Okay, sir.
Any other query? Any other question?
No, sir.
Anybody?
No, sir. No, sir. Clear.
All right. Then let's move to the next definition. That is the definition of continuous arc. Continuous arc. Continuous arc. Hmm. What is this continuous arc? Over here, you see any point on any point on this kind of two-dimensional plane. Hmm. Any point, if you consider, or any curve, hmm, any curve over here. In that case, an arbitrary point on that curve will have this kind of coordinate. Maybe the first is the coordinate of the point t, x of t, and second has the coordinate of this kind of point y of t. Hmm. Now, you see, we say that this kind of arc or curve, whatever you call, this kind of arc or curve, you see, in terms of complex number, this can be written as x of t in terms of complex number, x of t plus I into y of t, hmm, and that would be is equal to z of t. Hmm. So, any point on this kind of curve will have this type of representation. Hmm. So over here, this expression, this would be the mathematical expression of this kind of curve. Hmm. And we say that this curve is a continuous curve whenever it does not have any break, and mathematically it means that these two quantities x of t and y of t, this should be certain, this should be two continuous functions of the parameter t. Okay, this should be the continuous functions of the parameter t. If the parameter lies in between maybe a and b, suppose a is less than or is equal to t and less than is equal to b, and on this parameter, on this kind of interval, the functions x and y, if these two are continuous functions, then we say that this kind of curve represented by zt is equal to xt plus I into yt, then this kind of curve is called a continuous arc, or a continuous curve. Clear? So over here, continuous curve means their corresponding component functions x of t and y of t. These two component functions should be the continuous continuous functions of the parameter t in the corresponding domain of definition. Over here, a less than is equal to t less than is equal to b is the domain of definition of this kind of. Okay, so this is the definition of continuous arc or continuous curve. Now let me introduce another definition. Hmm. Over here, you see the second definition that we shall discuss over here is the definition of multiple point. Multiple point. What is this? Hmm. Multiple point means suppose we have a curve like this. So if the curve starts from the point A and suppose any point on the curve is represented by this kind of function, say z of t is equal to x of t plus I multiplied by y of t. All right. Now suppose as the time t or as the parameter t, not time, t suppose increases from a to the point small b. Hmm. So the parameter t is increasing from the point A. And suppose at the point A, t is equal to, at the point capital A, t is equal to suppose small a. Hmm. As the time increases, the any arbitrary point is moving along this direction. Fine. Now suppose when the curve is moving along this branch, hmm, it would come to this point. Suppose this is the point C. It would come to this point. Maybe say at the point t is equal to t1. Then the parameter value increases. Fine, and the corresponding point, any arbitrary point over here, again traverses this curve, and again at the second time the point comes over here again, and there the time is equal to t is equal to suppose t2. T is equal to t2. All right, and then it moves in this direction and finally reaches the point, say capital B, whenever t is equal to b, whenever say t is equal to b. All right, so what we observe over here, we observe that at t is equal to t1, t is equal to t1, the point lies on the point C. Again, at t is equal to t2, we again have this same point C. So C, we obtain this point C for more than two values of this parameter t. For more than two values of this parameter t, we obtain this point C. All right, and this kind of points are called multiple points. Whenever we have more than two values of the parameter t, such that at these more than one values of the parameter t, such that we obtain a single point for different values of the parameter t. We may have three different values of the parameter t, then the curve would look like this. So, whatever be the possible cases, at more than at more than one times for this parameter value, if we have or if we encounter a single point on the two-dimensional plane or on the complex plane, then such points are called multiple points. Okay, this kind of points are called multiple points, and associated with this definition we have one more definition, that is called the Jordan arc. What is Jordan arc? The Jordan arc says that the Jordan arc says that the any arc, if it is a continuous arc, continuous, hmm, if it is continuous, and along with that it does not have any multiple point, without multiple points. Without multiple points. Hmm? Without multiple points. If we have a continuous curve without multiple points, then such curves are called Jordan arc, or in some books it is also referred to as Jordan curve. Whatever you call Jordan arc or Jordan curve. So a Jordan curve is actually a continuous curve without any multiple point. It may look like this. Hmm. But remember, it does not have, it would never touch the curve again so that we get a multiple. Hmm. So such kind of curves are called Jordan curve. It may be very close to the original curve, but it would never touch. So it must be a continuous curve, and it should not have any multiple point. Hmm. It should not have any multiple point. So this kind of continuous curves without any multiple point is called a Jordan curve. Hmm. And along with these definitions, let me introduce one more definition. Hmm. Let me delete all of this. Uh, that is the next definition, that is called the definition of contour. As per your syllabus, we are to discuss the contouring here. So let me discuss or define what is called contour. Hmm? Contour is actually a finite chain of chain of Jordan curve. Or I forgot to mention you that this Jordan curve, hmm, this Jordan curve. What was Jordan curve? I forgot to mention one definition. Hmm. That in this Jordan curve means it would be continuous curve without any multiple points. So we expect that this can have this type of representation: z of t is equal to x of t plus I into y of t. As because it is continuous, therefore this functions x of t and the function y of t, these two functions should be a continuous function. But we now add one more condition, that is if along with continuity of these two functions x and y, if their derivatives x dash t and y dash t, if these two derivatives are also continuous, x dash t and y dash t, if these two derivatives are also continuous, then such curves are called regular curves or regular arc. Okay, regular curve or regular arc. I forgot to mention this definition, the definition of regular arc or regular curve. Hmm. So if x and these derivatives x dash and y dash are also continuous, then such curves are called regular curves. So Jordan curve, all these Jordan curves are not regular curves. If in the Jordan curve, if along with the continuity of x and y, if their derivatives are also continuous, x dash and y dash, then such derivatives are called regular arc. Hmm. Now, let me define this contour. Let me define this contour. What is contour? What is contour? Contour. Contour is actually it means that it would be a finite collection of continuous regular curve. Okay, it would be a finite collection of continuous regular curve. What this means? Say this is like this. If you consider this kind of curve, you see over here, say from A to the second point, suppose B, we have a continuous curve. Now from B to the point C, we have another continuous curve. From C to the point D, we have third continuous curve, and from D to this point E, suppose we have the fourth continuous curve. So this is curve number 1, this is curve number 2, this is curve number 3, and this is curve number 4. Now over here, you see this kind of bending over here at this point. This kind of sharp bending would say that you see this is this should be a Jordan curve. That means z of t. It would have this type of representation. Z of t is equal to x of t plus I into y of t. Over here from A to B we have a continuous curve. Fine. From B to B we have another continuous curve. All these curves are all continuous curves. From D to E all these curves are continuous curves. So over here this xt and yt, this curve should be continuous. But the problem is that whenever we have a sharp bending like this, in such bending this x dash t and y dash t, these derivatives would not be continuous. If these derivatives and this x dash and y dash should be continuous, then we will have this kind of bending, so that certain kind of tangent exists. All right, but whenever we have a sharp bending at this kind of point capital B, the tangent of the curve does not exist. That means this x dash and y dash would not be continuous at this kind of intermediate points, maybe at the point B, maybe at the point C, maybe at the point D. Okay, but otherwise these functions x dash t and y dash t would be continuous, so that the curve become a regular arc or regular curve, except at the point B, C, D, at this intermediate point, regular. All right. So except at the point B, C, and D, except at the intermediate points, the curve is actually a regular curve. But you can consider that in between A and B, it is regular curve. In between B and C, it is a regular curve, or you can say regular curve means a continuous Jordan curve. In between D and E, this is also regular curve, is also regular curve. So what we have, we find that from starting from A to B, we have one regular curve or regular arc, then the second regular arc, the third regular arc, the fourth regular arc. So we can consider this entire curve, as a finite collection or a finite chain. Why chain? Because they are connected by at this point B, then at the point C, then at the point D. So that's why we are calling them a chain. All right. So this is actually a finite chain or a continuous chain of regular arc. All right. So this kind of arcs are called contour. The definition of oriented curve. What is this oriented curve? Orientation, you might have heard this word about this orientation. What is this? Suppose we have a curve. Let me write or draw this curve in a three-dimensional space. Okay, this is z-axis, maybe this is the two-axis. Let me extend this z-axis in negative direction. Suppose this is our x-axis, this is our y-axis, and this is our z-axis. And let me draw the xy plane in this fashion. So this is our xy plane. Now you consider any curve. So this is our xy plane or the z, generally the Argand plane. I should not write z over here, because in that case this z refer the complex. Suppose these are the two axes. This x-axis and y-axis, and we are also considering a third axis. Whatever be the axis, it doesn't matter. Hmm? So let us denote this kind of curve. Let us denote this kind of curve over here. Let me break this one. Yes. Now, if you look at this curve from an observer, who is sitting up on this direction, in this positive direction. This an observer is looking from this direction. In that case, if this is the point capital A and this is the point capital B, in that case you see the observer would find that the curve is moving along this direction, maybe along this direction. However, if we have an observer sitting over here, if we have an observer sitting over here, and if he observes that yes, over here, he would find that the curve is moving in opposite direction. So from two different point of view, the observer will find that the curve is rotated along two different directions. Maybe along this direction from an observer from an observer from this direction, he would say that the curve is rotating along anti-clockwise direction. And from this kind of observer, he might say that the curve is rotating along clockwise direction. So that is called the orientation of that curve, and it depends upon the observer. Most of the times we consider the orientation of the curve from the point of view of this observer, so that if we consider these three axes, x-axis, y-axis, and say this is the maybe omega axis or w axis, I am not using the notation z, then x, y, and w, they will form a right-handed system of coordinates. This kind of directions are called, this kind of orientations are generally taken as positive orientation whenever it is anti-clockwise. Anti-clockwise orientation is taken as the positive orientation. All right. So remember that orientation from one direction would be positive and orientation from another direction would be negative. But the anti-clockwise orientation is mostly taken as the positive direction. And if the curve is considered to be the curve gamma, in that case, then a negatively oriented curve. That means say this is the curve, say from this direction. Maybe this is the anti-clockwise direction from A to this curve, this point B. Then if somebody says no, I would consider a curve from B to A. In that case, the second observer will designate the curve by negative of gamma. Just this negative sign comes in order to designate that the orientation is in clockwise direction. Okay, so plus gamma or simply gamma or negative of gamma, they may refer to a single curve depending upon the orientation. So in this curve, suppose in this curve t would increase from A to B, A less than is equal to T less than is equal to B. So T will increase from A to B. That is the if it is the direction of T, in that case, in case of minus gamma, T will decrease from B to A. Okay, that would be the direction of the parameters T. Okay, over here, in case of this positively oriented curve, if T increases, in case of negatively oriented curve, T will decrease. So that is the idea of oriented curve. Okay, and in this along with this direction, along with this notation, you need to remember that if the curve, if the initial point capital A and the final point capital B becomes same. That means if the starting point and the last final finishing point becomes same, say this is the point capital A and this is equal to the final point capital B, then such curves are called closed. Closed. So closed curve may have this kind of orientation, that means anti-clockwise orientation, or may have clockwise orientation. It depends upon the observer from which direction one is looking at the curve, from upper side or from lower side. Anyway, if A becomes is equal to B, then such curves will be represented by will be designated by closed curves. The idea of rectifiable curve. Roughly speaking, a rectifiable curve is a curve whose length is finite. That is a very rough definition. Rectifiable curve. Okay. So we can say that rectifiable curve is a curve whose length is finite. Now, how to mathematically define the idea of rectifiable curve? Suppose, let me draw this picture. Suppose this is a curve. Let me draw a simple curve. Right? Say this is a curve. Now we want to measure this length of this curve. If it is a bit complicated, maybe this kind of curve, then what would we do? Say from starting from the initial point capital A to this final point capital B, what would we do? We would consider this first point, and then very close to this point we will consider a second point, then the third point, the fourth point, and so on. We will try to consider or subdivide this length into very small segments, so that these small segments would look like a straight line. These segments would be so small that this kind of small segments would look like a straight line. Say the first point is equal to, suppose, z0. Then the next point, suppose this is our point z1. Then this point is equal to z2, and so on. And the final point, suppose this is equal to zn. Now, what would be the length? Let me draw this length by other color. Let me consider this blue color. And let me change this one. Suppose this is the length in between z0 and z1. Then how to write the length in between z0 and z1? We can simply say modulus of z1 minus z0, or you can also write it as modulus of z0 minus z1. It doesn't matter. So that would be the length in between the point z0 and z1. Now, what is z0? Suppose z0, you see we have a curve. So the curve would have this type of equation: x of t plus I into y of t, and we expect that a less than is equal to t less than is equal to b. Now at the point z0, suppose z, this z, okay, so I should write z as a function of t. At the point z0, this z becomes the function of t0, and at the point z1, suppose this z becomes the function of t1, and so on. Finally, at the point zn, this z becomes function of tn. Tn means over here, let me write it this b. Tn is equal to b. And what is this t0? T0 is actually equal to a. This t0 is equal to the point a. Okay. Now in that case, you see this is the length from the point z0 to z1. Then the second length would be is equal to modulus of z2 minus z1 and so on. Finally, the last length would be is equal to modulus of zn minus zn minus 1. Now, if you add all these lengths, if you add all these lengths, then we would get an approximate length of the curve in between A and B of this entire curve. All right. So what would be the approximate length of this entire curve? That would be is equal to summation, maybe from R is equal to 1 to n modulus of z r minus z r minus 1. This modulus would be an approximate length of this curve. And if we keep increasing this value n, that means if we keep increasing the number of points in between A and B, in that case we will get more and more accurate length of the entire curve. Let us denote this curve by gamma. So if this curve is finite, if this curve has a finite length, then taking this limit n tending to infinity, we will ultimately be able to reach the length of that curve L. So in order, as n tends to infinity, of course, n tends to infinity. So in order to have this kind of finite length, you see, we will find that this kind of expression, this total summation, will be bounded from above side, of course, and of course from lower side it is bounded by 0, because this is actually the length, summation of two lengths, so length can never be negative, so these quantities are all greater than is equal to 0. But if this is bounded, that means if this quantity is less than some finite number, suppose capital M, then we can say that yes, ultimately as a tending to infinity, ultimately this summation will have certain upper bound, and this summation will have certain limit, and that limit L is called the length of this kind of curve gamma. And if that length is finite, or in other words, if this summation is bounded above, if this summation is bounded above, then such curve is called a rectifiable curve. All right. If this summation is bounded above, then such curve is called a rectifiable curve, and this length is actually L. This L is actually in that case considered as the length of that rectifiable curve. So what is L? Elaborately speaking, that should be limit n tending to infinity of this summation modulus of zr minus zr minus 1. So modulus of this expression r is equal to 1 to infinity. Okay, so this length is this length will be designated, this L will be designated as the length of this rectifiable curve. And if this is finite, then only the curve is rectifiable. There, that's why I told you earlier that if a curve has a finite length, then that curve is called a rectifiable curve. Without introducing any mathematics, I gave you the definition. But mathematically or rigorously speaking, if this summation is bounded, then the curve is rectifiable, and in that case, this limit L would exist, and this limit is called the length of that rectifiable curve. So that is the definition I wanted to discuss with you. So that's all for this lecture. Thank you for being with us.